Okay, this is our last section of chapter 4. This is the first of the more advanced integration techniques. This is integration by parts. So we have one objective, and that is to solve problems using integration by parts. Using integration by parts. So I always like to go through where this technique comes from because it's something that we can actually understand. So every differentiation rule has a integration rule that undoes itself. Now, the last section we looked at substitution. Substitution is how we undo chain rule problems. Because if we were doing chain rule, then u would be a function. We would take the derivative of u, leave the inner, which would be whatever it is, and then the derivative of the inner. You look back at some of those examples, you can see where the chain rule was used if you were to check your work and take your derivatives. So when we're doing integration by parts, this is the companion integration rule to the product rule. So our product rule says the d dx of f times g is f prime g plus g prime f. Now if we combine that with 4.3, what we saw in 4.3, the fundamental theorem of calculus, which says the integral of d dx of f of x should equal f of x. Right? Integrals and derivatives undo themselves. So if we're taking the derivative of f of x and then we take the integral of that derivative, we should be right back where we started at f of x. So now we're going to combine that with the product rule. So this means that the integral of d dx of f times g should equal f times g. Hopefully we're all on board. Now, d dx of f times g is the product rule. And so we know that this is integral of d dx of f times g also equals the integral of f prime times g dx plus the integral of f g prime dx. Now, this means that these two things have to be equal. That f g prime, the integral of f g prime dx plus the integral of f prime g dx equals f times g. And so what we do here is we subtract this second piece away, and we have the integral of f g prime dx equals f times g minus the integral of f prime g dx. Now, if we let u equal f of x and v equal g of x, well, then we have the following. So for u equals f of x and v equals g of x, the integral of u dv equals uv minus the integral of v du, where dv is nothing more than g prime of x dx, since v is g of x, and du is nothing more than f prime of x dx, since u is f of x. And that's just coming straight from the last thing where we're doing substitutions. So this equation becomes our technique for integration by parts. So we have some examples here to integrate and to practice. What we have to do when we're solving problems with integration by parts is identify the parts. We pick the parts. So you always start by picking two specific parts. We pick u and we pick dv. That's what we always pick. So if we're looking at u dv, the idea is you pick your dv so that it's very easy to integrate. And you pick your u so that it's very easy to differentiate, find the derivative. So if we let u be x and dv be e to the x, then the derivative du, well, that's just dx, and the integral of dv, v, is just e to the x, because e to the x is easy to integrate and x is easy to differentiate. Now, when we do our integration by parts rule, this becomes uv x e to the x minus the integral of v e to the x dx. Now there's a really easy way to know if you've done this correctly. When you get to this step, this integral should be easier than the previous one. So I'm going to say that again. Your integral after you apply your parts equation, this rule here, should be easier than your initial integral. If it's harder, you've done it wrong. And by do it wrong, I mean you've probably picked the wrong u and the wrong dv. So watch what happens if I was to select the other way. Because some of you undoubtedly probably thought to yourself, well, e to the x is pretty easy to integrate, or pretty easy to differentiate, and x is pretty easy to integrate. Well, if u is e to the x and dv is x, that means du is e to the x dx, and v is x squared over 2. And so we end up with x squared over 2 e to the x minus the integral of v du, which is x squared over 2 e to the x dx. So if we're comparing, this integral is even harder than this integral, because now I have an x squared instead of just an x. So that's why we don't select that. So you can always compare. It's a relatively quick process to set up the integration by parts. And if your integral is harder, or a lot of times what we look for is the power to be reduced. So notice the degree of x went up instead of down. That's how you know you've done it right. And so this just becomes x e to the x minus e to the x plus c. Or if we want to get fancy, e to the x times x minus 1 plus c. Right? So our next problem here is we want to evaluate this. So picking our u and picking our dv. U is going to be x, dv is going to be ln of x. U is super easy to differentiate. Now, here's a pitfall of this problem. What's the antiderivative of ln of x? If you thought about it and you're not sure, the answer is not sure either. That's a hard question. So we actually don't want this. So this is another example of how to pick the right u and dv's. If you don't know the antiderivative of 1, don't pick that for dv. So now we're going to say u is ln of x and dv is x. That makes du equal to 1 over x dx. And that makes v equal to x squared over 2. And so our integral is uv ln x times x squared over 2 minus the integral of v du, which is x squared over 2 times 1 over x dx. And that's just going to be x over 2. So this is x squared ln x over 2 minus x squared over 4 plus c. So always be thinking about, first and foremost, is u easy to differentiate, and then is dv easy to integrate. And if your choice of u gives you something that you can't integrate easily, pick the other version. So let's look at this next one here. So here we have to make a choice, and we have to combine two functions. So I'm going to let u equal the top, x e to the x. Why? Because if dv is then 1 over x plus 1 quantity squared, then our v will be easy to integrate, relatively speaking, using a substitution, because this is just x plus 1 to the negative 2. So remember, the format is u dv. It has to be a multiplication. So once you pick your u, whatever's left over, not necessarily on a fraction. So du using the product rule is e to the x plus x e to the x all times dx. And v using a u substitution would just be negative x plus 1 to the negative 1. So our integral then is uv negative x e to the x over x plus 1 minus the integral of v du, which is e to the x times 1 plus x over negative 1 plus x. And I've rewritten it on purpose like this, dx. So now these cancel, and this is just negative x e to the x over x plus 1. Minus minus makes this plus. Antiderivative e to the x is just e to the x plus c. And that's our final answer for that problem. So I have two here for you to practice, so I recommend you pause the video and try this out. And I'll start going over them now. So x squared e to the x. I want my u to be x squared. I want my dv to be e to the x. And I want that because when I take derivatives, it will make this simpler. And when I take integrals of this, it's easy and it doesn't change anything. So v becomes e to the x. And du is 2x dx. So setting up my parts, we have uv x squared e to the x minus the integral of v du, which will be 2x e to the x dx. Now you may be looking at this and go, that's still not doable, but is it easier? And the answer is yes. We've reduced the power by 1. So what we actually have to do here is set up another parts, u1 and dv1. u1 is going to be 2x. dv1 is going to be e to the x. That makes du1 equal to 2 dx. And that makes v1 equal to e to the x still. So now we have x squared e to the x minus parentheses u1 v1 2x e to the x minus the integral of v du, which will be 2 e to the x dx. And now this integral is totally doable. So this is x squared e to the x minus 2x e to the x. And then this is minus a minus, which makes plus. Antiderivative of 2e to the x is 2e to the x plus c. And that's our final answer for that problem. So here we have a definite integral. Again, just like with substitution, these techniques They're not unique to indefinite integrals. So I'm going to pick u to equal x because it's easy to take the derivative of. That means dv is going to be x plus 5 to the negative 1/2 dx. So du is dx, and v then, using a substitution, we're essentially doing the integral of x plus 5 to the negative 1/2 dx. That's what we have to do real quick, and that's just going to be 2 times x plus 5 to the 1/2 because it's a power rule. And so then our integral becomes uv 2x times x plus 5 to the 1/2 minus the integral from 0 to 4 of 2 times x plus 5 to the 1/2 du is dx. And so this equals 2x times x plus 5 to the 1/2. X plus 5 to the 1/2 is going to give us 4/3 times x plus 5 to the 3/2. And now all of this gets evaluated from 0 to 4. So this is the one step that some people write this in right here. They do a 0 to 4 to remind themselves. Sometimes some people don't. But remember that this thing is equal to the antiderivative of this. So the evaluation has to happen at the end to everything. And so what this ends up becoming is, when you plug it all in, 4/3 times 5 square roots of 5 minus 9, and that's applying the fundamental theorem of evaluation. Plug in 4 and then plug in 0. Okay, so those are some challenging ones. This last problem is an application. So oil is produced from a well at an estimated rate of R of t equals 100 t to the negative 100 t e to the negative 0.1 t, where t is in years after production begins. We want to find an expression that represents total oil at the end of t years. So remember, we are finding total oil. So make a little note here. We are finding total oil and are given a rate. Essentially, we're given the velocity. So remember, s of t, s prime of t equals v of t. S is the position, right? From chapter 3, the derivative of position is velocity. Now, this can be extended to general rates of change. Remember, we extended this and we said s of t can just be any measurable thing. It's a quantity. The rate of change of that quantity is then the derivative. So we want the quantity. We want s of t. And right now we have v of t. Or in our case, we have r of t. So if r of t is our v of t, which is then s prime of t, or what we'll call t prime of t for total oil, what we need to do is integrate. We need to integrate t prime, which means we need to integrate r. And that will give us the t that we want. So we have the integral of 100 t e to the negative 0.1 t dt, which is 100 times the integral of t e to the negative 0.1 t dt. Hopefully you can see that this has to be parts because we have the multiplication of two functions. So I'm going to let u equal t, and I'm going to let dv equal e to the negative 0.1 t, or e to the negative 1/10 t That makes du just equal to dt, and that makes v equal to negative 10 e to the negative 0.1 t. So if you're confused where I got the negative 10, it's a substitution, or you can think of it as just correcting the constants like we did at the beginning of chapter 4. My derivative should have a negative 1/10. I don't have that negative 1/10, which means I need to multiply by the negative 10 to cancel it out when we go backwards. So take your derivative of v here, and notice that you're going to have negative 10 times negative 1/10, which will get us perfectly back to where we wanted. Now we can set up the parts. So we have 100 times the quantity. Remember, the parts equation is only good for the integral. So since I brought the 100 out, I have the integral. This is what becomes the parts equation. uv negative 10t e to the negative 0.1 t minus the integral v du negative 10 e to the negative 0.1 t dt. So this is 100 times negative 10 e, negative 10t e to the negative 0.1 t. Minus minus makes plus. 10, the antiderivative of e to the negative 0.1 t, we just did that once, is negative 10. So this becomes times negative 10 e to the negative 0.1 t. And all of this will be plus c at the end. So we have negative 1000 t e to the negative 0.1 t minus, this is 100 times 100 is 10,000. Excuse me. E to the negative 0.1 t plus c. And that would be our final answer. And remember, if we wanted to get rid of this plus c, we would need to have some sort of initial condition to plug in and get rid of the c. So this is how integration by parts works. As I said, this is the first of a few advanced techniques of integration that if you continue on and take another calculus course, this will be where you start. Most of those courses pick up with either substitution or with integration by parts. But this is the end of 4.6, and with it is the end of chapter 4 for us.